this lecture, we're going to talk about some odds and ends of graphing functions. We're going to talk about even and odd functions and what that means in terms of the graph if you know a function is even or odd. We're going to talk about how you graph piecewise defined functions. And we're going to talk about the greatest integer function, which is a special example of a piecewise defined function. Let's start with the definition of even and odd functions. We say that a function f is called even if f of the opposite of x equals f of x for every x in its domain. So another way to say this is if you plug in a negative number and then you plug in the opposite of that, the corresponding positive number, you always get the same result. And a function like this is going to have symmetry through the y-axis. For every point with a negative x-coordinate, there's going to be a point with a positive x-coordinate that mirrors it, where the mirror is the y-axis. So knowing that a function is even will tell you that the graph is symmetrical with respect to the y-axis, and you might use this for various reasons. If you're trying to graph a function and you know that it's even, then you can focus on finding points with positive x-coordinates, and the points with negative x-coordinates will just be the mirror image of that. There are tricks that we do in trigonometry and calculus that take advantage of knowing that certain functions are even. In this lecture, we're going to focus on determining whether or not a function is even, and maybe talking a little bit about its graph. We won't be able to do any of those upper level things. A function f is called odd if f of the opposite of x gives you the opposite of f of x for every x in its domain. So here, if you plug in two numbers that only differ by sign, same magnitude but different in sign, then you don't get the same output, you get opposite outputs. And this gives us symmetry through the origin. So here the mirror that you're reflecting through isn't a vertical line or a horizontal line even, it's just a point. You reflect through that point at the origin, the point 0, 0, and you get a mirror image point on the other side. This one's harder to imagine, so I'll show you a specific example of an odd function. Again, determining that a function is odd can help you graph it. There are also ideas in trigonometry and calculus where you apply the fact that you know that a function is odd. There is a third possibility, by the way. A function doesn't have to be even or odd. It can be neither. If it doesn't display symmetry through the y-axis, it doesn't display symmetry through the origin, then it's neither even nor odd. So let's look at an example. This says determine if the given function is even, odd, or neither. And the function we're looking at is f of x equals the square root of 16 minus x squared. I chose to do this example first because we can cheat on this example. Without having to do the algebra, we already know whether this function is even, odd, or neither. The graph of this function is a semicircle. It's the upper half of the circle of radius 4 centered about the origin. Every point on the left side of the graph has a mirror image point on the right side of the graph. Maybe my graph doesn't look perfect, but it should be that way. Even the points at the bottom, this is the point at negative 4, 0, and we've got this mirror image point at positive 4, 0. This function is symmetric with respect to the y-axis, and therefore it's going to be even. Here's how you show this without getting the graph. There's an algebra rule. It says plug the opposite of x into the function and simplify. If you get the same function you started with, then the function is even. So in this example, I'm going to evaluate f of the opposite of x and see what I get. I'm going to replace x with the opposite of x. Well, when you square the opposite of x, you get x squared. And this simplifies to the function that we started with. This simplifies to f of x. Since f of the opposite of x simplified to the original function, this function is even. And again, we already knew that this function was going to be even because we know what this graph looks like. Let's look at another example, and this time we'll start with a function that we're not as comfortable with. This says determine if the given function is even, odd, or neither, and the function is f of x equals x cubed minus 9x. Now, if this was x cubed minus 9, we'd know exactly what that looks like because that's just a vertical shift of one of our library functions. But the extra x on here puts this outside of the realm of what we've learned to do. The only way that we could graph this right now as a class is to plot a bunch of points. So with our current knowledge, we don't know if this is even, odd, or neither. Let's test. If it's even, then f of the opposite of x equals f of x. And if it's odd, then f of the opposite of x equals the opposite of f of x. Notice that both rules depend on evaluating f of the opposite of x. To determine whether this function is even, odd, or neither, I'm going to evaluate f of the opposite of x. I'm going to plug the opposite of x in for x in the function. So this becomes the opposite of x cubed minus 9 times the opposite of x. When we cube the opposite of x, that's 3 negative factors, so this will be negative. And of course, x to the third power is x cubed. When I take negative 9 times the opposite of x, that becomes plus 9x. And that's definitely not what we started with. You can see that it's different. This function is not even because this did not simplify to the function we started with. How do I determine if it's odd? It's if f of the opposite of x equals the opposite of f of x. Now, one way to interpret that is multiply the original function by negative 1 and see if it gives you your result from evaluating f of the opposite of x. I actually choose to do this a different way. I factor a negative 1 out of this expression, and I see what that gives me. So if I factor a negative 1 out, that gives me x cubed minus 9x. Hey, that's the original function. This is the opposite of the function that we started with. Since f of the opposite of x is equal to the opposite of f of x, this function is odd. Odd functions display symmetry with respect to the origin. And again, that might be hard to imagine, so I'm going to try to draw the picture here. If you find the x-intercepts of this graph by factoring and then consider the end behavior of this function, you get the graph that I show here. Notice that it's not symmetry through the y-axis or through the x-axis. Rather, it's symmetry through the origin. For every point in the first quadrant, there's a mirror point in the third quadrant passing through the origin like this. So if there's a point up here, I go through the origin, it translates to a point down here. And for every point in the second quadrant, there's a corresponding point in the fourth quadrant, again passing through the origin. I've got a point up here, it corresponds to a point in the fourth quadrant. That's what we mean by symmetry through the origin. In our class, learning that a function is odd really only tells us this aspect of the graph. But being able to show that functions are odd in future classes might be important, so make sure you practice the algebra. Let's look at one more example. This says f of x equals x squared minus 5x plus 4. We want to know if this function is even, odd, or neither. Pause the video and see if you can figure this out. The test for even functions and odd functions both depend on evaluating f of the opposite of x, so that's where I would start. I'm going to plug the opposite of x in for x in the function f. Each x gets replaced with the opposite of x. In the first term, the opposite of x squared just becomes x squared. A negative times a negative is a positive. In the second term, negative 5 times the opposite of x becomes plus 5x. Again, that's the product of two negatives. And then a plus 4. That's not the function we started with because the middle term is now plus 5x instead of minus 5x. So this function isn't even. And if I factor a negative 1 out of this, I get the negation of x squared minus 5x minus 4, and that expression inside the parentheses isn't the original function. I don't get exactly what I started with. I don't get the opposite of what I started with. This function is neither even nor odd. F of x isn't a graph that we could come up with translations, but we could just plot some points and figure this one out too. Because of the x squared, you can probably guess that it's a parabola. Because it's got a positive leading coefficient, you'd probably guess that it opens upward. If you don't know that yet, we're going to learn that in the future. If we were to factor this, there would be two x-intercepts, one at 1, 0 and one at 4, 0. And the graph would look something like this. You can see that it's not an even function by the symmetry rule because it's not symmetrical through the y-axis. You can see it's not an odd function because it doesn't display that symmetry through the origin. These points in quadrant 1 would have to have corresponding points in quadrant 3, but this function doesn't even touch quadrant 3. It's clearly not an odd function. This graph definitely has symmetry. It's just not through the y-axis and it's not through the origin. It's through this vertical line right here, which happens to be the line x equals 5 halves. But it's not an even function or an odd function. A function can still be symmetrical even though it's not even or odd. It's just not that special type of symmetry for an even function or an odd function. An even function is specifically symmetrical with respect to the y-axis. An odd function is specifically symmetrical with respect to the origin. This function is just symmetrical through some other vertical line, and so it's not even or odd. Okay, now we're going to shift gears and we're going to look at piecewise-defined functions. A piecewise-defined function is a function which follows different mathematical rules over separate parts of its domain. For some inputs you follow one rule, and for other inputs you follow another rule. And the way that you write a piecewise-defined function is typically to name the function and then use a set brace and contain the rules here inside the set brace. So you'll make a list of all of the different rules for the different pieces of the domain. I'll show you an example, and this is actually an example we're already familiar with. We didn't write it like this when we learned it. but we already know this function. This function f of x says the rule if x is greater than or equal to 0 is just output x. Whatever you plugged in comes right back out. But the rule says if x is less than 0, then our output is the opposite of x. So we're going to follow this rule a few times and see if we can identify what function this is. The first thing we need to find is f of 3. To evaluate a piecewise defined function, you actually want to start with these if parts, the conditions. That tells you which rule you're going to follow. Our input 3 is greater than or equal to 0, so we're following the first rule. And what does the first rule say to do? Whatever you've plugged in comes right back out. F of x equals x, so f of 3 would be equal to 3. Our second example says find f of negative 2. I start by seeing which if statement negative 2 satisfies. It's not greater than or equal to 0, doesn't satisfy the first rule. It is less than 0, we satisfy the second rule. And so we follow the second rule, which says take the opposite of the input. So I take the opposite of negative 2, and that's 2. See if you can evaluate f of negative 5. So we take the negative 5 and we see which rule it fits into, and it should only fit into 1. If it's a well-written function, it should only fit into 1. Remember that a function can only have one output for each input. So it would be a really weird scenario if your input followed 2 of the rules, and even if it did, it would have to give you the same answer or else the thing's not a function. So it only satisfies the second rule, and the second rule says to take the opposite of the input, and we get 5. Last one says f of 0. See if you can evaluate f of 0. We follow the first rule. X is greater than or equal to 0. And we get x there. So f of 0 is 0. So it looks like this function leaves positive numbers alone, it left 0 alone, and it changes negative numbers into positive numbers. Do you recognize the function? Yeah, this f of x is just the absolute value of x. The absolute value of x is an example of a piecewise defined function. We have a notation to describe it, but it really works in pieces. If the input is non-negative, we follow one rule, and if it's negative, we follow another rule. That's an example of a piecewise defined function. Let's look at a second example, but this time a function that we're not familiar with. This function is also split into 2 rules. It says that f of x is equal to x squared if x is less than or equal to 2, and that f of x equals 2x minus 5 if x is greater than 2. This is kind of a weird rule. This isn't a very real-world scenario. If you're wondering where piecewise defined functions would come up in the real world, a good example of it is the tax codes, the tax laws. For different incomes, there are different rules. We call those tax brackets, right? So you pay a different percentage of your taxable income based on which bracket you fall in. Real-world examples like that have too many different rules for us to start with those. So we have to do examples like this to begin. So while this isn't a real-world example, this is an easier example than what you would use in the real world. So we have to evaluate the function at 3 different inputs, negative 3, 4, and 2, and we're going to follow the same rules we did in the last one. We're going to start by seeing which rule applies to our input, and then we're going to follow the rule. So for example, to evaluate f of negative 3, I see which rule it fits under. Well, negative 3 is less than or equal to 2, and so I follow the rule for those inputs, which is to square the input. So I square negative 3, and I get positive 9. To find f of 4, I identify which rule 4 falls under. Well, 4 is greater than 2. So I follow the rule which says take 2 times the input and then subtract 5. 8 minus 5 is 3. F of 2 is the only one you could really trip up on, but notice that 2 only satisfies one of these rules as well. 2 is not bigger than itself. No number is bigger than itself. 2 is less than or equal to 2, because 2 is equal to 2. So we follow the first rule. We square the input, and we get 4. So as long as you're careful, evaluating a piecewise defined function isn't difficult. Graphing a piecewise defined function can be a little bit tricky if you've never seen it before. Let's do a couple examples of that, and we'll start by graphing this very function. We're going to sketch the graph of f of x equals x squared if x is less than or equal to 2, and 2x minus 5 if x is greater than 2. You want to graph these functions in pieces. We're going to graph the first piece over this domain, over this interval, then we'll stop, and we'll graph the second piece over its interval. And of course you can do that in either order. It doesn't matter which ones you graph first. I'm going to start by graphing the first rule. We know that f of x is equal to x squared if x is less than or equal to 2. Now we're in luck here because we know what f of x equals x squared looks like. It's a parabola. But before you get jumpy and graph the entire parabola, like this, remember that we're only graphing this for x values less than or equal to 2. So what I've drawn here is incorrect. A common mistake is that I'll have students graph this function by graphing the first piece and second piece completely. That clearly fails the vertical line test, so that doesn't work. We're only going to graph this function up to the point where x equals 2. What I would do is give myself a target. Plug 2 into the function and see what you get. We already know what we get. We did that on the previous slide. F of 2 is equal to 4. So I'm going to plot the point at 2, 4. That's my target. That's where I'm going to stop on the right side. I'm going to graph that parabola y equals x squared up to the point where x equals 2. I missed the origin here. Let me just cheat. And there's the graph of the first piece of the function. For x values less than or equal to 2, this is the graph of y equals x squared. For x values greater than 2, we have to graph the function f of x equals 2x minus 5. Now that's not one of our library functions, but we still know what it looks like. That's a linear function, and so its graph will be a line. It's a line with slope 2 and y-intercept negative 5, but before you plot the point at 0, negative 5, remember that we don't follow this rule when x is 0. We follow the first rule. We already have a point there. If you plot a second point down at 0, negative 5, you're going to fail the vertical line test. That won't be a function. We need to plug in numbers greater than 2. Now the obvious thing to plug in, I guess, would be to plug in 3 and to plug in 4. We plugged in 4 on the previous slide and got 3. If you plug in 3, you'll get 2 times 3 minus 5, which is 1. And now we have 2 points that we can plot. We can plot 3, 1 and 4, 3. And we know we're following a line in this direction, so that part's easy. But we also have to go back in the other direction, because you can't skip over numbers like 2.5 and 2.1 and 2.01 and 2.0001. Those are all inputs to the second piece as well. So I'm going to trace this back to the x-coordinate 2 and draw an obnoxious open circle there to indicate that there's not really a point. Now I just kind of freehanded that and didn't really figure out where it is. How would I actually figure out where that hole is? This is where that arrow notation comes into play. What I really want to know is what happens as x approaches 2 from the right. This is asking what would happen if we picked a number that's just barely bigger than 2. Well, we would plug that into the second rule, because that's the rule you use for inputs bigger than 2. And what would f of x approach? Well, it would approach what you would get when you actually plugged 2 into the rule. I know you're not allowed to plug 2 into the rule, but when you're plugging in numbers like 2.00000001, you're practically plugging in 2. There's a negligible difference between those. So if I were to plug 2 into this rule, I would get negative 1. And that's how I figure out where the hole should really be. We're not trying to get a perfect graph, so I just kind of freehanded it, but you could figure out exactly where that hole is. It's at 2, negative 1. You have to draw it as an open circle so that this passes the vertical line test. Let's try graphing a second example, and this time our example will have 3 pieces. So in this example, if x is less than or equal to negative 1, then the output is just the constant 3. Any input less than or equal to negative 1, the answer is always 3. If you have an input between negative 1 and 1, then the output will be the cube of the input. And if your input is greater than or equal to 1, then the output will be determined by negative 2x plus 3. So we're going to graph this in pieces. We could make a table of values off to the side, but I think these pieces are easy enough to graph without doing that. Like, consider the first piece. If the input is less than or equal to negative 1, then the output is 3. So at negative 1, the output is 3. And at negative 2, the output is 3. And at negative 3, the output will be 3. And on this left side, we're going to get a horizontal line. That's the line y equals 3. But it stops at x equals negative 1 because that's where that rule ends. As soon as we get past negative 1, we switch to the second rule. And that second rule happens to be one of our library functions. It's f of x equals x cubed. It only applies from negative 1 to 1, and it doesn't even include those bounds. So we know what x cubed looks like. It's that one that snakes through the origin, but we can't draw that entire graph. We're only drawing the piece from negative 1 to 1. So it would start down here with an open circle because we don't include the point at negative 1. And it snakes through the origin until I get to the point where x equals 1. So let me give myself something to aim for. So the graph would look something like this. And then when I get to 1, I get another open circle. If you want to figure out where those open circles are, you just plug -1 and +1 into the second rule. I know you're not allowed to do that for the function, but we're really considering that one-sided behavior. Now here's an interesting thing about this function. When we get to x equals 1, we switch rules. But notice what the output is. When I plug 1 into the function, let me write this one out. When I plug 1 into the function, I get -2 times 1 plus 3, which also happens to be 1. The same thing you get when you plug 1 into the second rule. So that open circle gets filled in when we evaluate f of 1. One more point should do the trick because we know this is a line. F of 2 would be -2 times 2 plus 3. That's -1. So f of 2 is -1. I'll plot that point. And we get this line here. We know that's a line. This is like f of x equals mx plus b. So here are the two rules joined up at that same spot. Those of you who head towards calculus will use examples like this to discuss continuity. You can see that there's a discontinuity at x equals -1. There's this big jump in the graph. But at x equals 1, the two pieces matched up. They met up at the same point, and so the function is continuous on that side. We're going to do one more piecewise defined function, but it's a special function that has its own notation, just like the absolute value function has its own notation. This one gets used often enough in computer programming that it has its own notation. And that's the reason why I want to do this one. I've reached out a lot to the calculus students. I've done some business examples to try to get the business people worked in. I haven't done anything for the programming people, for the computer scientists. And so this is a function that you'll use a lot in computer science. It's called the greatest integer function. The greatest integer function is basically a round down function. It says we define the symbol, and I've used this notation where you kind of draw a floor underneath the x. If you look in a textbook, it's usually typeset a little bit differently. It's got like a double bracket around it, but I can't draw it very well. And so the nerds have decided that this is a reasonable way to write it. Just draw a little floor underneath it. Anyway, here's how we define that notation. It says for an input x, the greatest integer function will output a value n, where n is the greatest integer such that n is less than or equal to x. So it rounds down to the next smallest integer, unless you're already at an integer, and then it leaves it alone. I know that's kind of confusing to say, so we're going to do some examples. So let's evaluate each of these four. Here we're applying the greatest integer function to the input 7.6. This function rounds down. Let me go back to the rule. It says n is the greatest integer such that n is less than or equal to x. Well, what's the greatest integer that's smaller than 7.6? Well, it's 7. So this rounds down to 7. You have to be careful with the negative number. To apply the greatest integer function to -1.2, you want to find the first integer that's less than or equal to -1.2. You're not going to round up to -1, you round down to -2. If you're having a hard time seeing that, I want you to imagine where -1.2 falls on the number line. Right? Here's -1.2. It's surrounded by two integers. -1 is bigger and -2 is smaller. And what does the rule say? Always jump to the greatest integer that's less than or equal to your x value. So I have to jump down to -2. That's the first integer that you run into as you move to the left. If the input is already an integer, you leave it alone. That's where the or equal to comes in. N is the greatest integer, the biggest integer, such that n is less than or equal to x. Well, -8 is the biggest integer that's less than or equal to -8. So you stop there. You do not take that one down. See if you can apply the greatest integer function to pi. Most of you probably know at least 3 digits of pi, 3.14, and that's all you really need to know. Well, you're going to take that to the first integer that falls below it, which is 3. More generally, the greatest integer function is a piecewise defined function with infinitely many rules. We don't write it this way because it's such a pain, but here's basically what it says. I've written some of those rules out. Let's start with a couple of the positive ones because they're easier to see. If you have an input that's between 2 and 3, including 2 but not including 3, you're always going to round those down to 2. Think about what x values would fall on here. It'd be numbers like 2.5 and 2.7 and 2.9 and 2.3 and 2.048 and 2.99975. Those all get rounded down to 2. And of course 2 itself stays at 2. That's why we want the or equal to here. If we had a number that was smaller than 2, then we'd use a different rule. And as long as that number is bounded between 1 and 2, including 1, then the output will be 1. Numbers like 1.2 and 1.5 and 1.8 and 1.9 and even 1 itself. If the number is between 0 and 1, the output will be 0, and so on. You could follow this rule forever. It says infinitely many pieces. Again, this gets used in computer programming. I've done very little computer programming, and even I've used this before. If you're into older movies and you've seen Office Space, which is a favorite of mine, they run this scheme where they round off the remainders from bank transactions into an account. And of course, I can't say for sure how that program was written, but that sure sounds like a greatest integer function. Rounding down the interest transactions sounds like a greatest integer function application to me. So if you ever write a piece of software that's going to rip off the company you're working for, maybe you'll use a greatest integer function there. I want to show you what the graph of this would look like. Remember that this section is essentially about graphing. So I want to show you the graph of this function. It's a weird one because it's got so many rules. I'm actually going to use this description to help me graph it. Let me start with the rule at 0. We'll just start in the center of all of my rules. It says if the input is between 0 and 1, not including 1, the output is 0. So let me mark where x equals 1 is. And starting at 0, the output is 0. And for all of the numbers between 0 and 1, the output is 0. And when I get to 1, the rule changes. When I get to 1, the output jumps up to 1. So that's going to give me a point up here at 1, 1. And then the rule says the output continues to be 1 until you get to 2. So the outputs are consistently 1 until I get to x equals 2. And then when I get to 2, the rule changes again. It says for x equals 2, up to and not including 3, the output will be 2. And the output stays the same until I get to 3. And you can imagine it's going to keep doing that. And even does that in the opposite direction. I'm not going to bore you with too many more examples, but let's just do one more. For inputs between -1 and 0, not including 0, the output is -1. So if I go over to -1, the output is -1, and that continues until I get to 0. Obviously, it can't be the same there because that wouldn't be a function. And we continue to get this as well. And so because of this, this is sometimes called a step function. Let me draw these in here. If I draw in these vertical lines, which are not part of the graph, I'm just doing this for fun, it looks like a set of steps. I'm immediately going to erase those so you don't think that's part of the graph. As you can see, this looks like a set of steps. It's called a step function. Kind of a weird graph, but you can see where it comes from. Okay, we ran through a couple of different ideas here. We had even and odd functions and the symmetry that's displayed by those types of functions in their graphs. And then piecewise defined functions where we evaluated them, we graphed a couple, and then we looked at a couple of special examples, the absolute value function and the greatest integer function. That's it for this video. If you have any questions for me, don't be afraid to contact me. You can catch me in an office hour or shoot me an email.